In this video, I'm going to talk about how to draw a ray diagram for a convex mirror and how to use the mirror equation to locate the image. So first, I have a convex mirror and the focal length of this mirror is 4 centimeters if we were on the concave side. But I'm going to put an object here on the convex side. It's going to be 5 centimeters from the mirror, and I'm going to do two things. I'm going to draw the ray diagram to locate the image, and I'm going to calculate di quantitatively. So for the ray diagram, I'm going to draw, as we usually have done, a line that's a light ray that's parallel to the principal axis. And when it hits the principal axis, it's going to bounce off. Now this convex mirror here is a little straight and not exactly convex, but I do know that a light ray would go, if it were a lens, it would go through that focal point, and so the light ray would go out like this. It would bounce off. So for a focal length of 4, the curvature of this mirror would be such that this line would go right off, and if I had a normal and a tangent line, I'd have angle of incidence equal angle of reflection. So what you can do, and this is not exactly straight, but I can trace it back to where it would go through, and then I get the reflected light ray. The other light ray, as we've seen, is going to contact the mirror, or right down here. And for that given angle, we're going to come down the same amount. It's going to reflect off approximately like that. Now, since these two light rays don't meet, it's a virtual image we're probably going to get. And in addition, this is a virtual focal point. So when we do the calculation for our DI, we'll see how that affects our number. Basically, it's going to be negative. At any rate, to locate the image, I take the reflected ray, which I know goes to the focal point, which I've already done, and I take the other one, and I go back like this. And so here I get my image, which you'd expect to be smaller, because it's a convex mirror. And now we're going to calculate where exactly that's at. So there's the ray diagram. So for the solution of the quantitative part, I'm going to list my equation. 1 over F equals 1 over DI plus 1 over DO. The variables here, focal, DO, and DI. So this is a virtual focal point. So this is going to be negative 4 centimeters, not positive 4 as we've done in the past with concave mirrors. DO, as in the given, it's 5 centimeters away. And I need to find DI. So I'm going to use the same 5-step process for the solution. A, B, C, D, and E to keep everything organized. So 1 over F is equal to 1 over DO plus 1 over DI. I think I flipped the order here, but it's just addition. So since we have a virtual focal point, this is going to be negative 4. 1 over 5 plus 1 over DI. This is going to be negative 0.25 equals 0.2, positive 0.2 plus 1 over DI. Then if I bring the 0.2 over, I'm going to get negative 0.45 is equal to 1 over DI. But again, I don't want 1 over DI, I want DI itself. So if I invert and multiply, negative 2.22, I believe, centimeters. And then box your answer. So you can see I get a negative number here because it's a virtual image. 2.2 is the answer. And so 2.2, which is approximately right here, should be the distance it is away from the mirror itself. So in this problem, we drew a ray diagram for a convex mirror and used the mirror equation, which is the same as the lens equation, to locate the image, noting that the easiest way to find this reflected ray, if you don't have a perfectly curved mirror here, is to just trace back where it would go through to the focal point, and then draw it back outwards. If you have a perfectly drawn mirror, you could draw a tangent line and a normal, and you would get the exact same result.